This is Computer Programming 1 from the University of Washington. I'm Martin Dickey, and today we'll continue our discussion of functions in Lecture 8. Although I've titled the lecture Function Parameters, parameters are only one of many important topics we'll talk about today. In addition to parameters, we'll be talking about return values, return types, the return statement, local variables, function prototypes, and header files. There's tons of new terminology in this lecture as well. Toward the end of the lecture, I'll do an extended example with an actual program traced in detail. And following that, I think there will be time for a couple of bonus topics that I think you may find useful when you sit down to write your programs. Let's go back to the example we used extensively last time. A function which prints a banner of 2 lines. It's quite a simple function. One of the advantages of functions, one of our primary motivations, was to make programs easier to change in case the designer or the client finds a need to do that. Let's consider one of these changes and see how it might affect us and how we might handle it. Suppose the client now decides 2 rows is not enough. There should be 5 rows of asterisks when the program starts and stops. But all the other times, there should be only 2. How could we solve this problem? Well, using what you know now, you could sit down and write a second function, maybe call it print banner 2. That function could print 5 rows of asterisks. And then back in the main program, you would call it at the beginning of the program, call it at the end, and in all the other spots you would still have calls to the original functions. You could do that, but computer scientists are notorious for always trying to generalize, to find an abstraction that covers more than one case. Could we generalize here? Could we somehow take a single function, print banner lines, and make it do both of the operations that we need? Make it print 5 lines sometimes and make it print 2 lines other times. In essence, that's what parameters are all about. And a great deal of the lecture will be devoted to showing how we can do that, some of the consequences, and some of the programming details involved. Let's state the problem in a slightly different way. Our original specification was to print 2 rows of asterisks. We'd like to modify that so that it could either print 2 rows or 5 rows. A more general way of stating this would be, let's print n rows, where n is some quantity that we don't know ahead of time. It might be 2, it might be 5. Maybe it could even be something else. At the moment the function is called, that value would be known, so the function would know what to do. So n, this number, is information that the function needs to know, and that's a crucial concept. We need a way of getting information into the function. Let's suppose there is a way to do that. I won't show you the code for it right now, but let's suppose we could do that. How would that change our main program? Here's how it would look when I call the new version of print banner lines. When I want to print 5 lines, I would put that requested value in parentheses following the function name. Now pause a minute and try to remember what was there originally. What did I used to have instead of parenthesis 5? If you remember or go back and look, it used to be a parenthesis with nothing inside, just an empty parenthesis. Okay. The parenthesis is there to hold the information that's being sent to the function. And we have a name for that kind of information. It's called a parameter. This is terminology we will now use extensively in the rest of the course. A parameter, information that is to be sent to the function. How would we write this function? I'm not going to give you full code now. It's not really relevant what the function body is doing, and we'll see other examples later on in this lecture. The crucial thing is the beginning of the function, how the function knows what information to look for. And this is done in a way that's rather parallel to the function call. We still have the function name, print banner lines, but now in parentheses we have something that looks like a declaration. It says int n. Think back to what was there before. It was not an empty parenthesis before, it was a magic keyword void. I briefly said that void meant we're not sending information and there are no parameters. Now there is a parameter. We want the function to know a value. So what we do is we declare what we'll call a formal parameter. We'll give it a name and we'll give it a type. It's exactly the same format I use when I declare a variable in the program. And it does declare n. It declares a location whose name is n and whose type is int. The special or magic thing about this n is that when the function starts to execute, it will contain in n the value sent to the function by the program that calls it. Let's take another application and see a different example of writing a function. Suppose we're asked to write a function that computes the area of a circle. Okay. Well, there are a couple of things buried in that specification. One is that the answer depends upon what the radius is. So we'll need to give information to the function. That should suggest to you the concept that was just introduced, a parameter. This function will need a parameter. We'll need to know what the radius is. But there's another new wrinkle here too. Because after the function has computed the value, somehow it needs to communicate that value back to the calling part of the program. So we didn't have this in the print banner. All we had was passing information via a parameter to the function. Now we're also trying to get information back. This new wrinkle is called a return value. You can see that a return value is a complementary notion to that of a parameter. When we execute a function, we send information to it with the parameters. When that function is finished, it returns the value back to us. Let's look at the code for this, the complete code. Now, I've done a lot of talking, and so you might expect that the program would be long and complicated, but it isn't at all. The program is extremely simple. Here it is. We're declaring a function, and you see the two key parts of that, as before, are the function name and the function body. The function body are the statements enclosed in the curly braces. Things look more elaborate now because we have parameters and return types. The word double in front of area is a familiar word. That's our old friend, the keyword that says we're defining a type, a value of type double. Okay. What we're doing here is defining the return values type. So by writing the word double in front of the function name, I'm saying this function returns a value of type double. Now in parenthesis, I have a double R. By coincidence, the type of the parameter is the same as the type of the return value. Here I'm saying that the function will receive a value, it will be placed in R, and it will be of type double. So those two features are complementary, sending information and getting it back. Okay. If a parameter, if a return value is part of the function, then there will be a type given in front of the function name. There will not be the keyword void as we had with the print banner lines function. Sometimes we call such functions non-void functions, or we call them value returning functions, just to emphasize the fact that they're giving data back, that they don't have a void return. Here's a new function to look at, or at least part of one. It has a slightly different breakdown of communication with the rest of the program. We can tell that by looking at it. The function's name is genRandom. Now let me ask you some questions. Does this function return a value? And how do you know? Well, your first instinct might be to look through the function body and see what it's doing, but you don't have to do that. You know that information from the first line. Sometimes we call that line the header. The first line starts with double. That means that the function returns a value and that that value's type is double. Does this function take a parameter? Does it get value? The answer is no. And how do you know that? You look at what's in parentheses, the parameter list. If there are no parameters being passed, the keyword void is there, and we see that this time. So here we have a function which does return a value, but it doesn't get one. So somehow it's making up a value out of thin air, some sort of random number. We have one technicality to worry about in the programming, and that is, once we've thought up this number or this calculation, how do we get it back to the program that called it? And the answer is by using a new type of statement called return. This statement was actually present on the previous slide. I did not point it out. Let's look at it here. The last line of the function body says return result. Because this line is in the program at this point, the function genRandom will stop executing, and whatever value is in the memory location of result will be given back to the program that called it. The return is a new statement type. It is a keyword in C. Its use is to terminate the execution of the function and also to give a value back if the function returns a value. How does the calling part of the program see the result? Okay. That's fairly important to know. Let's look at this example of a main function that is calling genRandom. It calls it twice, in fact, on the third line of the main function body. Remember, main is just a function. Okay. Third line of the main function body, we see an assignment statement. All assignment statements are evaluated according to the same procedure. We start with the right-hand side, completely evaluate it, figure out what its value is, then we take that value and put it into the variable whose name is on the left-hand side. Let's apply that principle to the third line of this program. What we should do to understand the assignment statement is go to the right-hand side. And what does it say? It says genRandom, empty parentheses. That is a function call. So we're right here in the middle of trying to do an assignment statement, and we've got a function call. When the system sees this, it will stop executing in main. It will go off to the genRandom function and perform all of its statements. Now, at the end of that statement, function, as we just saw, there's a return statement. That will send the value back. Where does it come? Well, one way to think of it is that the value sent back completely replaces the genRandom call. So if genRandom sent back, say, 35.2, this assignment statement essentially now says first random gets 35.2. The program isn't actually changed, but that's the way it's going to operate. So now the assignment statement would be completed by taking 35.2 and storing it into first random. Okay. Let's go on to the next line of the program. What happens there? Well, it's pretty similar. We do the assignment statement by looking at the right-hand side. That's a call to genRandom. That will send back a value. That value then will be assigned, that is, placed into the variable named second random. An interesting thing here is that the two calls to this function, genRandom, are completely separate from one another. They don't influence each other in any way. genRandom will always start at its beginning and always execute its statements, okay, uninfluenced by what might have happened a few milliseconds ago when the function had been called again. It's almost as if there's a brand new copy of GenRandom that was just created and is now being performed. This material can sometimes be a little bit of a brain twister. So here are some questions that I'm going to pose. I'm not going to read them or answer them in this lecture. But what I suggest you do instead is stop now and think about them, or later on come back and consider each one of these questions. Make sure you understand it and then try to work through an answer. You can get the answer purely from what we've discussed so far. You do not need to go to a reference book or look up abstract details, things we haven't covered. All of these questions are answerable from the principle we've had now. You might do this in the privacy of your own padded cell, or you might want to get together with a group of fellow students and do this. If you can come up with answers that seem plausible, you're in good shape. If you can't, this is a sign that you might want to go back and review this material and give it a little more thought, because all of these principles will be applying again and again as we add to the concepts with more and more terminology and ideas. Let's go on then and look at this process with the caller and the callee side by side. The process of sending a parameter value to a function is a kind of a matching problem. We're taking the data from one place and we're sending it to another, and we want to make sure that the right data gets there. Now, if the function has only one parameter, then the matching isn't a very complex problem. However, it is important that if the function has a parameter defined, then when you call it, there must be a value sent. Sometimes we call the value that's being sent the argument rather than the parameter. Okay. So it would be a mistake to try to call area with empty parentheses. That won't work. The function area is expecting one and exactly one parameter. It's also expecting that parameter to be of the type double, because that's the way it is declared. And so the value passed in had better be double. Let's check and see if it is in this case. The value of the parameter is whatever z over 2.0 is. That's an expression. We need to go back and look at what z is. Z looks like a double. I'm guessing that because it has a decimal point in it. So a double operation will be performed. That value, which is 49 point something, you can check me if you have a calculator, that value then is what is sent to the parameter named r. Everywhere inside the program, where, to be more specific, everywhere inside the function area, during that execution of area, the value of r will be 49 point whatever. There's a little bit of terminology confusion. Some textbooks use the word formal parameter for what you see in the function definition. They use actual parameter instead of argument for the value you pass when you call. Generally in these slides I'll try to stick to parameter for the definition and argument for the call. Another piece of terminology that I may have used already because it's very, very common is that when you replace the parameter with the argument, that is when you actually send the data in, this is called passing the argument to the function. Okay? Or, just to get practice in using this terminology, passing the argument to the parameter, or passing the actual parameter to the formal parameter. All of those convey the same information to people who are familiar with functions and their use. Let's step back and see where we are. Why were we doing this? Well, long ago we said that a new type of control flow would be useful, that sequential flow was great, and conditional flow was great, but it would sure be nice to have a way to break out of that flow, go somewhere else, do something, and come back. We've now seen all of the major technical aspects of that, and we can give a more detailed account of exactly how this flow works. Understanding this is often useful when you're trying to debug your own program and things are not working right. As part of the process of tracing the program, having a detailed knowledge of how this control flow goes will often be helpful. What we will do after going through a little more of this detailed material is take an example, and I'll do that with you. So you'll see what to do on your own when you have a trace like that to do. So here are the steps that happen. Some of these are interesting technically, but it's not necessarily important to know all the details of how they work. To begin with, the function is called by the caller. I would like to use that terminology from now on. The caller is the place in the program where the function is called. Memory space has to be found for that function's parameters and local variables. Say more about local variables later. The system does that automatically. You don't have to think about it except to know that it's happening. That memory will be provided for those parameters. Then the values being passed are copied from your area, your variables, your expressions, to that new memory that the function will have access to. Once that has been done, the control of execution, the CPU's thread of execution, can then be transferred into the statements of the function, starting at its first statement and continuing. Now, necessarily in order? Well, yes and no, because that function may use sequential control flow, or it could use conditional. It could also use functional control flow and do function calls itself. So we will be following the control flow according to the statements of that function. When that function finally finishes, then the CPU has to be sent back to the caller, the calling location or site in the program. All of this is handled automatically for you by the system or by the operating system. You don't have to think about how it works too hard, but it's often very helpful to have a mental picture that it is happening. Let's look at it in a concrete example. Here I'm calling our familiar function area from a main function. Actually, I'm calling it at two different locations. The first time, it's about the third line down, I say x gets area, and then in parentheses y over y times 3. Sometimes people read those parentheses as sub from mathematical notation, area sub y over 3, or area of any notation that makes it clear verbally that this is a parameter value being passed. What happens at this point, as we know, is the function will be called, and what you see there with the red line is meant to be the hotline of the CPU, where the CPU is actually in the code. So the red line has been following the main program at first. Now, as a result of the call, the red line shifts over to the statements in the body of the area function. It follows them through, and when that function finishes by its return statement, the red line hops back over right to where it left off and continues from that point. Okay. Later on in the program, I call area again, and that red line would hop over to area again, except I thought the lines would be too confusing if they were both red. So I've changed the color to blue here, but it's that same line. It's that thread of execution, the control flow, flowing over to the function body of area, going through it for a while, and then coming back. And as it comes back, you see the value. And think of that as being carried, perhaps, by the return, coming back and being available for the value of that function in the expression. Now notice in that second case, the call to area is only part of a larger expression. So when I get back from that function, I'm still in the middle of the assignment statement. And the next thing that will be done is 3.4 times 194.976. That's the next operation that would be done. And when that's done, then the assignment completes by storing that value into Z. Then the thread of execution, that blue line, continues for the rest of the statements in the function main. And from now on, instead of saying program all the time, you're going to hear me use the word function. Because C programs really are collections of functions, and that's the way programmers think of them. So instead of saying that the program calls something, I'll probably start saying the function calls something. The picture is the same. A few style points. There are certain rules you have to follow when you declare a function. You have to have the return type and the name and the parameter list and the double quotes. The comments above the function are ignored because comments are always ignored by the C compiler. But they're not ignored by people who read the program. So if you were writing a program for me, I would not only expect you to get all the punctuation and the C syntax right that the compiler expects, I would also expect to see a comment there. And I really would expect to be a comment that was relevant and succinct and told me information that I would find helpful if I was using the function. Here's a good test for whether you've written a good comment. Cover up everything except the comment. Cover up the program itself. Sorry, I want to say function from now on. Cover up the function. And then ask yourself, is there enough information in the function that in the comment that I would understand what the function is doing and how to use it without having to look at the code itself? Okay. There should be enough information in the comment and the first line of the function so that you don't ever have to look at the function body if all you want to do is call the function. Okay. Now, this is a matter of syntax. No, it's a matter of style. But it's one that is widely accepted among the programming community. We've seen the idea of parameters as information being passed into a function. The material between the parentheses can contain more than one parameter. We could have a list there. Actually, we've seen that already too. Can you think where? In an earlier lecture, we had lists of something that really were parameters. And that was for printf and scanf. Remember, those are functions. And when we talked about using printf and scanf, we said, well, we have a control string, then we have a list of expressions or a list of variables. Those are simply parameters because scanf and printf are simply functions, although there are some special things about printf and scanf. The big rule is this. If the function has more than one parameter, then when you call the function, the arguments you pass it have to match. They have to match in three ways: in number, order, and type. Okay. Boy, it sounds a little bit like learning Latin grammar. The adjective has to agree with the noun in case, gender, and number. And it really is a very similar process. Okay. Number means if the function is expecting 3 parameters, then you have to pass it 3 parameters. Order means they have to be in the same order you've defined them. You can't mix them up. And finally, the types have to match. As we've seen, there are many, many places in C where types are critical, where the compiler cares a lot about what the types are, where the compiler is going to check to see that types are matched up and are compatible. And this is one of those. It's a really important place where that happens. Let's look at this example. On the right, we see a function named average. How many parameters does it take? 2. So when I call it, left-hand side, how many parameters must there be exactly? There must be 2. Let's do a little more with this one. The first parameter of the function is of type double. How do we know that? Which side do we look at, by the way? Left or right-hand side to determine that? You should be looking at the right-hand side. That's where the function's defined. That tells you what the expected type is. Have we done it right when we called it on the left-hand side? GPT is the name of the variable. What is GPT? We looked back up earlier in the function. Aha, it's a double. So that's okay. We've matched the functions in type. Okay. So you must get this right. The C compiler will usually complain, but not always, and especially on really old versions of C, compiler did not complain, and you could do really terrible things by not having the matching done right. Let's see where we are now. At this point, we've seen all the basic concepts for how a function communicates. What do I mean by communicate? That is how it gets data, how it passes data back. We've seen a lot of the technical detail for that, essentially all of that technical detail. And we know the syntax involved as well as the logical concepts. So logical concepts that are in some sense more important because we have to understand them, but it's the syntax that we have to have perfectly right when we sit down to write the program. There still is one technical concept that I'd like to show you before we go into our big trace. Alluded to it already, and that is the use of local variables. A function can define variables within itself. These locals or local variables have meaning only inside that one function. They're not usable in any other function in the program. So picture this. A typical C program is not just main and one function off to the side. The typical C program may be dozens or hundreds, yes, or thousands of functions. Inside each of those functions, there may be local variables defined, but each local variable can be used only inside the particular function where it's defined. Okay. Parameters are also considered local in the sense that the name you give to a parameter is something you use inside that function only. In a sense, this is not new information. What about the functions we've seen so far? What about main? What about the variables we've seen there? Are they special? They're not special. The truth is, the variables we've been using so far are all local variables. Every single one we've seen in this course has been a local variable, usually a local variable of main. So there's nothing really special or new here. It's just that we're becoming more aware of the complete environment that we're programming in. And here's a function other than main that has a local variable in it. It's circle area implemented in just a little bit different way. It achieves the same result, but it does it by using some intermediate assignment statements. And in those intermediate statements, we have local variables. You might want to take a look at this later on at your leisure and just make sure all of this makes sense. Why do we have a special terminology for local variables if that's all there is? Well, the answer is that isn't really all there is. There is another type called a global variable. And I almost hesitate to mention, I almost want to suggest that you should put your fingers in your ears during this part of the lecture and not hear it at all, and also cover your eyes so you won't even see this concept. That's what I would recommend to my own students. It is possible to declare variables outside of a function, and these are global variables. Global variables do have legitimate uses in a language like C. But when I make assignments for this course in the on-campus version here at the University of Washington, I do not let my beginning students use global variables. Period. Under no circumstances will I let a beginner use global variables. The problem is that they can very quickly become a crutch, because with global variables you can avoid using parameters in certain cases, and often students find parameters so difficult that they're looking for ways to avoid it. I'm betting that you won't have that problem, that you'll take my warning seriously, and that also you're going to be a model student and you're going to go back and review parameters and understand them perfectly anyway. So you won't need a crutch like that. You might wonder if the pound-to-find symbols also come under this ban. The answer is they do not. They are global in a sense, but they're not technically variables, and in any case they have so many advantages that we actually encourage their use. Let's quickly summarize what we've seen about global variables. Variables declared in a function are local to it, as are the parameters of the function. They can't be accessed except by that named function. Now, an interesting thing is that these variables don't really sit around there in memory all the time while your program is execution. The system doesn't find or allocate memory space for them until that function is called. Then it finds space, we call that allocation. The function can use that memory space for those local things. But as soon as the function returns, that variable space is given back. It's not needed anymore because the function is out of execution. And we'll see that in the trace that we're going to do shortly. Okay, let's take a deep breath. We have now seen everything we need, all the big concepts, all the little details, and everything in between to do a trace of a real program that involves some non-trivial function calls and returns. So let's start setting that up. The problem is going to be find the area of a washer-shaped figure. There's a picture of it there on the right-hand side of the screen. So this might be a little physical device with a hole cut in the center like a donut or a metallic washer. Our problem is to find the area of the ring, that is the area between those two concentric circles, the green part. Okay? So just take a minute and think about that from a geometric point of view. What kind of algorithm would you do? I'm not asking about a program yet, but what about just the general mathematical approach to this? Well, probably what you'd come up with is something like this. Find the area of the outer circle, find the area of the inner circle, and then subtract them. That should give you the remaining part, which is in green. Okay. We've got an algorithm now. So let's think about putting it into C. You could code this up in a single main function and execute it. But I'm not going to let you do that because I want to practice with functions. So we're going to break this down into a bunch of functions, one of which is already coded. It's the circle area function that I had up just a minute ago. But we'll have a couple of additional functions. One is a function to compute the area itself. Let's look at this briefly. Before we even look at the function body, we should ask ourselves, what information does the function need to do its job? By definition, those are the parameters. Well, this function will need to know both of the sizes of those circles. It will need to know the inner and the outer. Okay, so it looks like I need two parameters. Because we're dealing with physical measured objects, it looks like a double is probably the right choice rather than an integer. Once I've made those decisions, I can start writing the code to implement the algorithm. I need the area of both of those things. Okay. Now I could get the area by writing the formula, pi r squared. But didn't I already do that? Don't I have a function called circle area? Why not use that to do this? That's what functions are all about. Writing code once, solving the problem once, putting it in a function, and then using that function, calling it by name when you need it. So let's do that. Let's follow our own guidelines. And within washer area, we'll call circle area twice with different pieces of information. Once we've done that, if we save away the data, then we can do the subtraction, and we'll have an answer. Now, what do we do with that answer? Well, send it back. Send it back to who? We don't know, and you know, we don't really care. Washer area shouldn't care who called it. All it knows is it has some information, it has a job to do, it's going to do it, give the data back, throw it over the wall, and then disappear. Is this a complete program? Well, no, because we have to answer the question of where these radiuses come from. To do that, the logical thing is to design a main function that gets the information, say, asks the user for it. We know how to do that now. We know how to do scanfs. We know how to display the information with printfs. So our main function would call upon both of these two functions that I've put here for review, circle area and washer area, and then call upon printf and scanf to do the input and output for us. Now I'm about to trace this program. I think what you'll find helpful is to take a copy of the program from somewhere and have that physically in hand. Perhaps keep one finger on the program as I talk about it, maybe one eye on the program and the other eye pointed at the screen, something like that. That will make it much easier to follow what I'm about to do. And I've done the same thing. I have a copy of it here, and so if you see me looking down or trying to look in two directions at once, that's what I'll be doing too. Okay. All right. Tracing this program is really no different in theory from tracing other programs we've seen in this course. Remember the rectangle area one we did a while ago and tracing the Fahrenheit to Celsius. The principle there was to keep track of the variables in some sort of a table. Okay? And then step through each statement of the program to see what effect that has. The new wrinkle here is that with functions, we have more things to keep track of. The variables are going to be in different places, and the control flow is going to be bouncing around from one place to another. But the general principle is still going to help us. Another thing that would help us will be to depict the relationship between the functions. This is a kind of chart that we'll use again. What it shows are the functions only mentioned by name with arrows between functions that call one another. Okay? So you may want to check this with your printed copy as I talk about it. If you look at that copy, you'll see that main calls washer area, printf, and scanf. So I've got the arrows drawn to show that. Washer area calls circle area. That's the only function it calls. If you look within circle area, you'll see it doesn't call anything. So that's the bottom of our picture. Printf and scanf are off somewhere where we can't look at them, so we don't bother to try to make any picture below them. This is sometimes called a static call graph. With large programs, this is often very valuable way of trying to understand the program, see how the pieces fit together. By the way, this is another example of a tree, something we've seen before as a way of organizing and presenting information. Okay, so the basic tables I'll need will be one for each function. In main, I have 3 local variables to keep track of. In washer area, I have 2 parameters to keep track of and 3 local variables. In circle area, I have 1 parameter, r, and I have 2 local variables. We'll have to keep track of all of these. Okay. Well, let's get started. My goal is to step through main and keep track of what happens as I go in and out of the functions. Where will execution start? With the printf. Does that change any of our variables? No. What about the scanf? Well, yes. Scanf will change them. So at this point in my program, I should bring up the table for main. Initially, when these variables are declared, they don't have any value. So we could have written a question mark in here to indicate that. After the scanf, inner and outer both have values. Where'd they come from? Well, the user decided, I want to do this for a circle with an inner area of 2 and an outer diameter of 10. The inner is the radius, the outer is the diameter. What's why? We don't know yet. Okay. The next line in the program is a call to washer area. So at this point, I need to switch my focus of attention to the function body for washer area and the variables that it has access to. Inner and outer are its parameters, and they now have values. If you look back at the call from main, you'll see that the first parameter was main's inner, and the second parameter, although it may seem strange, is the outer variable over 2, 10 over 2. Okay. That may seem strange, but we have to follow the program as it was written. Now, within washer area, what do? Well, we do a little bit of stepping down, and then we make a call to the circle area function. Now, we're going to have to pause, take our attention out of washer area to circle area. Initially, its local values are unknown, but as soon as we call it, there's a 2 there in R. That was passed to it from washer area. Okay. Some of this may seem a little obscure if you're just watching this as a TV program. The way to clarify it is to take this piece of paper with the program on it and see what's happening in the program at each step. As you'll see, if you do that, y, the local variable in circle area, gets the square of R. And then there's a calculation multiplying by pi to get 12. Now, wait a minute. Is that right? 4 times pi is 12? Well, depends on your definition of pi, doesn't it? Pi is really 3.1415 something, but if you look at the program carefully, you'll find a little surprise. We defined it as 3, and that's just so it would be easier on me. I wouldn't have to do the multiplication in my head. So there's how we get circle area. Now, a critical thing happens for the control flow of this program. Circle area completes execution. Let's look at that within circle area. We've computed the area, and now we have the statement return area. What happens at this point is circle area goes away. It's done. The value of area is passed back, and the assignment statement can now be completed in washer area. So look, circle area is completely off the map. It's not there anymore. That local variable area is gone. Okay. Okay. Next, we're going to call circle area again. We get a fresh copy of it. Now, this is interesting. I just had values there, but where are they? They're gone. That old copy is nowhere to be found. We're starting all over again with circle area. And we could trace through 5, 25, 75. Again, we're at the end of the circle area function. That value gets passed back. It can complete the assignment statement for washer area. Now washer area has the information it needs. It can compute the actual area of the washer by doing that subtraction. We're now at the end of washer area, and we go back to main. And we're still on that assignment statement, y gets. Except now, I know what that value is from the washer area call. It's the 63. It gets stored there, and that changes the picture from main. We now have a y stored there. Okay, well, I don't know about you, but I think that's about as much mental activity on functions as anybody should have to do in one day. So we're going to skip the bonus subjects for today, and I want to give you a summary of functions. We'll come back and do some more topics at a later time on this. Functions can take several parameters or none, and we now know that as a concept and as syntax. Functions can return a value or none, and we know the concept and syntax of that. Functions are really valuable. We'll talk a lot more as we go along about other things that functions can do for us in terms of our mental process and our problem solving. There's a lot to learn yet about functions, both from this conceptual standpoint of their use as a problem-solving tool, and also some nitty-gritty topics dealing with how parameters are passed. We'll have these in, I believe, 2 separate lectures that will be coming up. A lot of students find functions challenging, but it is absolutely essential to master them. I really advise you do not try to go on in this course without making sure you have a firm understanding of all the material up to this point. The extra time and effort you spend now will repay itself greatly in your ability to succeed in the rest of this course. I hope that you find the information interesting and useful and not just challenging. I certainly do. And I hope you'll stick with me for the rest of the course. Please join me at the next lecture.